Joe or Joseph White. His talk is about mapping, cartography of open grassy ecosystems. The floor is yours.
Thank you very much, Pat. Thank you very much for the opportunity to be speaking today and for all of you in attendance. I'll be giving a brief background on how we plan to map open ecosystems in the GCBC project. So I'll first start my talk by saying that there are currently quite a few grassland maps that exist for Madagascar. However, there are a lot of important motivations for why we need a new and improved, more detailed map of Madagascar's open ecosystems. So firstly, to start off, just to outline that these grassy systems cover more than half of Madagascar's landmass, and that most Malagasy people live in the Central Highlands region, which fall within these grassy systems. These systems, because of their extent, are crucial for carbon sequestration, both within the grassland soils as well as in the context of the forest mosaics found within them. And there's huge potential across these grasslands and rangelands for zebra production. And within this context, it's also crucial to try and identify the species and regions which we can keep aside for grassland conservation. So a better understanding of the Madagascar grasslands will help provide us with a huge opportunity for strategic resource management. So just to go over the project goals again, and all of these link back to mapping in some shape or form, and trying to understand where a lot of these activities should take place. So firstly, we want to try and identify areas that are beneficial for tree planting, places where there's a high likelihood that trees will survive once they're planted, and this will help achieve some of these carbon goals for the project. Secondly, trying to identify areas within the grasslands that are not ideal for tree planting, but perhaps may be very good for zebra production. And that's going to be trying to aim at the livelihood aspects of the project. And then we'd like to try and identify these high biodiverse or species-rich areas of grassland, which we could set aside for grassland conservation and benefit biodiversity overall. And of course, all of these different goals are linked and connected to one another. So for example, areas that are used for tree planting can also be valuable for biodiversity, of course, if we're planting native local trees to these areas. So just a quick background on some of the different global and regional vegetation maps that have been produced. I'm just going to go through two kind of recent ones. And what you can see is many of these areas, I just kind of took out the different grassy areas in these maps. These are commonly used in big studies. And Madagascar is frequently not, or at least the grassy systems within Madagascar, are frequently not identified in these maps. You can see a very small area of Erica heathland in the Central Highlands that's identified here in the Dixon map. We have the same for the Dynasty map, where Madagascar's grassy systems are not accurately mapped. And then in the Global Typologies paper that Caroline introduced earlier, this is one of the first kind of global maps that probably recognize these grassy systems and recognize the fire dependence that many of these grasses have. And then of course there's the more detailed Madagascar Vegetation Atlas produced by Moten Smith together with a lot of Madagascar colleagues. And this did a really good job at identifying these central grassland regions using remote sensing and a lot of field data. A common theme throughout these maps is that they take years of collaboration to collect all the data, the field data, to try and put them together. So one of the objectives of this project was to see if we can try and produce detailed, replicable, and improvable maps for the vegetation for Madagascar's vegetation for spatial planning. The emphasis there being on replicable and improvable as more data becomes available. So the approach that we are attempting with the study is based on using plant growth forms. So again, linking back to some of the themes that Caroline mentioned, looking at function and processes. So there's already this absolute treasure trove of data that's been collected across Madagascar from many, many years of plant collections that are in herbariums, or more recently in programs like, or applications like iNaturalist, both from Madagascar scientists and international scientists. And using this data set and breaking it down into different plant growth forms, so for example, grasses, forbs, shrubs and trees, just relatively simplified categories. and combining this with different factors we know about the environment, for example, the climate as well as soils. We can use modeling to try and identify suitability maps for these different growth forms and try and map these across Madagascar. Combining these together, if we combine these 4 different suitabilities for these simplified growth forms, we can produce a vegetation map of Madagascar. I'd like to draw your attention towards just these 3 categories, 5, 6, and 7, and just show this figure on the right-hand side to try and show what kind of information we're then able to pull out of these maps. So units 5, 6, and 7 shows us that grasses are far more suitable in these regions. And these regions, similar to the Moulton-Smith map, cover the central highlands of Madagascar. Obviously, there's still a strong forb or herb component as well as shrub and trees. These areas are not only dominated by grasses, but it's quite clear that these areas in the central highlands and parts of western Madagascar are really favorable or suitable for grasses over other growth forms in particular. So using this approach to mapping, importantly, is reproducible. We can then extract lists of observed species from the direct observations that we had as input data, as well as using the predictions. Essentially we have a map of each individual species that goes into this, so it includes thousands of species across Madagascar, and we can use that for assessing the suitability for individual species. We can then combine these in different ways to produce biodiversity metrics across many different types of biodiversity, phylogenetic, functional, or simply kind of alpha diversity, the species richness of each site. And as I mentioned before, the real value of this is that it can improve as more data becomes available. There's still a lot of data sitting in herbariums across the world. One of the elements of this project is going to be trying to extract important information on location of species that is yet to be pulled into these databases. So just to try and pull back to those 3 themes, if we're basically essentially able to use this map to try and identify areas within these grassy sites that may be valuable for different tree species. So for example, we can pull out information from an individual tree and understand its broad suitability map. That can help us guide where to plant trees in these grassy landscapes. We can also map different grass species as well as their relevant characteristics, such as their value for pastures, understanding the carbon to nitrogen ratios, for example, and we can create a map of those grass species across Madagascar, which would be really important for zebra production and improving rural livelihoods. And then using the biodiversity metrics, together with the extensive plot data collected from the Global Grassy Group, for example, we can identify high biodiverse grassland patches, which can be excluded from these other land uses that we're focusing on, to help identification, for example, of key biodiversity areas or important plant areas to help achieve goals for global biodiversity frameworks. So if we to just extract these grass-dominated vegetation types, we can come up with a kind of simplified map of these grass-dominated regions. But I'm sure many of you will notice that this doesn't entirely resolve the nature of some of these forest grassland mosaics due to the spatial scale that we use, typically about 1 kilometer for these kind of maps. So just an example, within this grassy map we have Ivoiboro, which quite obviously has some grassy patches, but within this are mosaics of forest, really important large forest patches, which isn't resolved in our map necessarily. And there's a lot of theory behind topography. Again, Caroline mentioned this, she has covered a lot of this in her talk, and Leanne's going to cover a lot more of this and how fire relates to this a bit later. But the important topography and fire interactions that can help determine where you find these forest patches within grasslands. So one of the approaches to complement these broader scale grassland maps is to try and use modeling approaches with topography. For example, the curvature of different areas. Most of the forest shares often occurs in these kind of concave areas within the landscape. And we can then produce these forest suitability maps. And these can be done in much better resolutions, under 100 meters, which can provide far more detailed information to complement these broader scale maps that we'll be producing. So just to wrap that up, We want to try and produce this map that will be open, it will be collaborative, built together with Madagascar scientists. The analysis and tools that are going to be made to produce these maps will be open, so anyone can run these analyses on their own computers. And overall, we're going to hope to contribute to these goals of improving carbon, livelihoods, and biodiversity, and importantly, trying to tie these all together into a single usable platform to try and improve the strategic resource management of these grassland systems. Thank you.